Hey, we're gonna tackle from the AP Calculus AP exam free response 2010 number 1. So let's jump into it and try to knock this out in less than 15 minutes. All right, so we have Janet's driveway. There's no snow, and snow begins to fall at midnight. So from midnight to 9 a.m., you have snow accumulating on the driveway at this rate in cubic feet per hour, where T is measured in hours since midnight. Janet doesn't start removing snow until 6 a.m. And that rate that she's removing the snow is given by this G of T. And again, that's in cubic feet per hour. So basically what we have happening here, I'm just going to draw a little picture. Okay, it's snowing. And we have snow accumulating. Here's a little snowman. Okay, and we have snow coming down, and that's represented at a rate of F of T. And we have snow being removed, and that's at a rate G of T. Okay. Part A says to find how many cubic feet of snow have accumulated on the driveway by 6 a.m. So by 6 a.m., she hasn't started removing any of the snow. So the good news is that I'm only integrating F of T, because this is the rate that it's coming down. If I do the rate times the change in time, that'll give me total snow. If you think about it, this is cubic feet per hour for F of T. dt is delta T, or the change in time, so multiplying by hours, and those would cancel and give me cubic feet. So I put this in my calculator and I integrate it from 0 to 6 a.m. Put that in your calculator. I'm not going to show how to do that. You should be able to do that in the calculator, and I'm trying to keep this under 15 minutes. This is approximately 142.274 or 5 cubic feet. So that's part A. Okay, part B. Find the rate of change of the volume of the snow on the driveway at 8 a.m. Okay, so V equals total volume of snow. And I want the rate of change of that. So before I tackle the rate of change, I really need to come up with an equation for the total volume of the snow. So I'm going to say V of T is equal to, well, there's no snow at the beginning, so there's no initial amount I have to put there. But we have snow coming down. And I need to know how much total snow went down, and I need to know how much total snow was removed. And that'll account for how much total snow is left here in this middle pile. So I'm going to integrate F of T, actually. It's for any time t. So this is going to go from 0 to t. So this is going to be f of x minus g of x dx. Okay, if my upper limit is t for any time t, then the variables can't stay t in here. All right, now I want the rate of change of the volume on the snow. So that means I need to take the derivative of this. So I'm going to take the derivative of both sides. V of t, d dt of this. And on the left side, this is just V prime of t. And on the right side, I'm employing the second part of the fundamental theorem. And the way I recognize that is, one, I'm taking the derivative with respect to a variable of an integral, and the integral I'm taking the derivative of, the variable that I'm taking the derivative with respect to, which is t, is also present up here. Okay, so I have that same variable here. So the second part of fundamental theorem says I take this variable and I plug it into my equations here. So that would be f of t minus g of t. And then I would multiply by the derivative of this variable, which is 1. So that's redundant. There's no point in me writing that. But I want the rate at 8 a.m. So that's after 8 hours. So I have to find v prime of 8, which means I find f of 8, and I can find that easily in the calculator by putting the equation under y equals in the calculator and scrolling to the table and finding the y value, or manually plugging it in. And then I need g of 8. Okay, so again, to save time, I'm not going to show plugging that into the calculator, but g of 8 I get from the table. And if I want to find at 8 a.m. the rate of the snow removal, I have to use this one, because 8 falls between 7 and 9. So I have to use this part of the piecewise function. And if I subtract those two, I should end up with negative 59, approximately negative 59.582 or 3, depending on your calculator, cubic feet per hour. Okay, moving on to part C. That should make sense. It's cubic feet per hour because it's the rate for the volume, and volume is in cubic feet. Part C, let H of T represent the total amount of snow in cubic feet that Janet has removed from the driveway at time T hours after midnight. Express H as a piecewise defined function with domain from 0 to 9. Okay, so I'm basically integrating this. So I'm going to break this up into pieces. Okay. Try to leave space. So the first part of my piecewise function is 0. So H of T, I'm going to integrate from 0 to T, 0. Okay. ds. I'm just picking any dummy variable I want. I could put d, x, whatever. So I want a general equation just for that first part of the piecewise function. So this is for 0 to 6, that time interval. Okay, so by definition, the fundamental theorem says that, actually, I should write it like this. It would be h of t minus h of 0, right? And then I would move the h of 0 to the other side by addition. 0 ds. But there is no snow on the driveway, so that's 0. So I'm basically integrating this. And when I integrate it, if the antiderivative was, if I took the derivative of something and it was 0, then that means that it was some constant to begin with. And I end up with 0. Okay. Okay, so now I'm going to switch colors and do the other part of the piecewise function. So the other part of the piecewise function, the domain was from 6 to 7. And I am integrating from 6 to sometime t, because anytime t I'm speaking generally. So I'm putting the first part of my interval there. And I'm going to put the equation, which was 125 ds. Now, based on the fundamental theorem, by definition, that would be h of t. Let me try to make some more room here. By definition, that would be h of t minus h of 6. So that means that h of t is equal to h of 6 plus the integral from 6 to t of 125 ds. So h of 6 is total snow that was removed from the driveway. So far, she hasn't removed anything. Okay, just like that's why here, so far she hadn't removed anything, so it should make sense that this was 0. So I basically have, I can ignore that part. This is 0. And then I'm going to integrate this. So if I were to integrate this, this would be 125 s, and I would integrate it from 6 to t, which would give me 125. I mean, and that's just literally a coefficient that I could pull out. And then I would have t minus 6, and that would be h of t. So now I'm going to switch colors here, give myself some more room. Now I'm going to do the last part of the piecewise, which that part of the interval was from 7 to 9. Okay, so I would integrate the third part of the piecewise function, which is 108 ds, and I would integrate it from 7 to sometime t, which would not exceed 9. And by definition, by the fundamental theorem, that would be h of t minus h of 7. So then h of t would equal h of 7 plus the integral of 108 ds from 7 to t. Now, h of 7 is just 125. Where am I getting that from? Okay, so I'm going to use this, right? H of 7 is going to be 125 times 7 minus 6, which gives me 125. That's going to go here. So this is 125 plus, let me move that down so there's more room. Now I'm going to integrate this. So this is 108 t. And actually no, 108 s. And I'm going to integrate that from 7 to t. So now if I were to clean that up, remember this is just a coefficient, so I have 125 plus 108 times, I would plug in t minus 7. And that's my h of t equation for that part. So all I have to do now at this point is to condense all this into a nice piecewise function. So I'm going to say, okay, well, h of t, let me give myself more room. So h of t is equal to, and I have 0, and I have 125 times the quantity t minus 6, and then I have 125 plus 108 times the quantity t minus 7, and then I just put the limits of integration, not the limits of integration, but the domain. So this is from starting at 0 and ending at 6, and then right after 6 a.m. is when she starts to remove the snow. So that's why this is including up to 6. And then this one, okay, it goes from 6, after 6 up until 7, and then after 7 a.m., that's when we transition to the other equation, and that goes up to including 9 a.m. And that's your piecewise function. Okay. Okay, so the last part of this is they want to know how many cubic feet of snow on the driveway at 9 a.m. All right, so this is actually a lot easier than we think. So the total amount of snow, remember the total amount of snow is equal to the integral of f minus of f minus g. Okay, so the total amount of snow we know is the integral of f minus g. Okay, and I'm abusing notation here. But anyway, so if I want the total amount of snow at the 9th hour, then I'm going to integrate f from 0 to 9. That'll give me the total snow that was removed. Okay, f of t dt. But then when I integrate g, remember that the integral of g is equal to h. So that would be minus h of 9. Okay, and the reason why this is just h of 9 is if I'm integrating, let me just go back. If I'm integrating this, I can break this up into two integrals, and then the integral from 0 to 9 of g would be h of 9 minus h of 0, but h of 0 is equal to 0 according to this piecewise function. So now I put this into the calculator, and then I plug in 9 into this equation, and I have the integral from 0 to 9 of f of t dt minus, and I'm just going to do 125 plus 108 times 9 minus 7, which is this one right here. Remember, this is the one I have to use because this is the domain that it fits in this piecewise. And then you end up with the final answer, which is approximately 26.334 or 5, and that's cubic feet.